Okay, so today's lesson is going to be on efficiency. And efficiency, very simply, is how well energy that is put in is converted into the work we want a system or object to perform. Right? Is any machine, system, energy conversion 100% efficient? No. Okay? Because nothing is 100% efficient, energy flows from the high energy area to where? Yeah, which is usually the surroundings. Okay? That's because of which law of thermodynamics? The second law. Okay? The second law says energy flows from high to low, specifically hot to cold, if we're talking about thermal energy, which is usually the waste form of energy, okay, that all systems produce. Okay? What are some other waste forms of energy?
Sound and heat.
Sound, okay, and heat's thermal, right? So thermal and sound are two very, very common ones. Okay?
Light.
Light can be another one for sure. Okay? Those are probably your big three. Okay? Heat being by far the biggest, sound probably being a close second. Okay? Those do not perform a lot of useful work and are thus usually considered waste forms of energy. So when we're trying to make something more efficient, we try to reduce the things that cause those things to happen. So if we're looking at something that's moving, because that's usually what it does when it's doing work, okay, what are some ways we might make that more efficient? Or let me put it a different way. What force is probably most responsible for reducing efficiency? Friction. Friction comes in a variety of forms. Friction can be the direct contact friction between two surfaces. Okay? They're trying to slide past each other, and that's difficult. It can also be air resistance. That is, after all, still two surfaces trying to slide past each other. One's just a fluid. Okay? The air being the fluid. So air resistance is also a form of friction. That's obviously the most common, right? Anytime you have two surfaces rubbing together, trying to slide past, there's friction. How can I reduce friction? Okay, so right now, I'm trying to push my hands past each other. It's really, really hard. Okay, why? What could I do that would make them go past each other more easily? Because I can actually make them go past each other more easily if I don't do something I was doing the first time.
Don't put in work.
Well, I'm still putting in, I'm putting in just as much work.
Don't use some force.
Right, what's different? Like, I'm using the same amount of force either way. It's which direction. Okay? If I push my hands together and try and slide them past each other, there's way more friction than if I just do this. Okay? So what we want to do is try and make the places where the two surfaces are hitting each other have less pressure between them. The more pressure there is, the more friction there is. It's why you throw hay bales or sandbags in the back of a truck in the wintertime. The extra weight pushes the tires down onto the road and creates more friction. Okay? In case you ever wondered why we do that. Okay? That's the science behind it. The more weight there is pushing down on the tires against the road, the more friction you generate. Okay? So I could make sure that the pressure between the surfaces is less. What could I put between the surfaces? Something,
What?
yeah, something wet or slippery, okay? Like in engines, what do you put in your engine? Yeah, oil, okay? Oil's really important for your engine, okay? If your engine runs out of oil, it will die in glorious fashion, okay? And you definitely don't want that, right? So you put oil in an engine because you have metal parts, okay? A piston inside a cylinder that is moving up and down, right? There's metal on metal. And if there's no oil in there, okay, you get a lot more heat. And when there's a lot more heat, the metal expands and makes that pressure even greater, more and more friction, until parts of your engine just destroy themselves, okay, and try to exit the motor, right, making big holes in it through which oil and other important fluids will leave, okay, yeah, and that'll be the end of it, okay. If your motor seizes, that's what happens if it doesn't have oil in it, okay, you can't fix that, okay, it's done, So we need to have ways to reduce forces that cause us to lose efficiency. Okay, another way, because I was saying if you get too much heat, you get too much friction, you get too much heat and the metal expands, we keep it cool. Okay, keeping things cooler means that they don't expand as much. That's why your car has a cooling system on it. Okay, cooling system is really important. If your engine gets too hot, it doesn't matter how much oil is in it, the expansion will just become too great for the oil to do its job. Okay, that making some sense? All right, so if you went, let's say you went to urgent care. Let's say you were sick. You went to urgent care, and they said, okay, well, we have two doctors here. Doctor number one is right 95% of the time. I'd probably even say that wouldn't be really acceptable, but let's say that. Let's say he's right 95% of the time. And Dr. B is right 10% of the time. Which doctor do you want to go to? Yeah, you wouldn't accept 10% of the time being good enough, right? What about 14%? Still not good enough, right? You'd never accept something that was only good or only did 14% of its job. Except you do it every day. You get in a vehicle and come to school. Now, unless you have an electric vehicle or a hybrid vehicle. Okay? If you get on the bus, which is not a hybrid and it's not electric, okay, or you get in a car that just has a simple internal combustion engine, you accept 14% efficiency. That's good enough. Okay? Now, we've done a lot of things to improve the efficiency of the internal combustion engine over the years. It's probably more than 14% now. It's probably more like 20, even maybe 24, 25. Okay? But it's still not a great number. I mean, you wouldn't want to get 25% on a test. Okay? But every day, you accept that your car only converts 25% of the energy in its fuel into useful work. Okay? Let me put it to you another way. You may not have done this yet, but I've done it lots of times. Put $100 worth of gas in your car, which is easy to do when gas costs as much as it does right now. Okay? You have a truck like me, and it just seems like the thing will never be full. Okay? Chug-a-lug, chug-a-lug, chug-a-lug. Okay? You put $100 worth of gas in, knowing that 75% of that money, $75 of that $100 is going to go up in smoke and do nothing. And that's if all you do is actually drive it. That doesn't include if you just sit there and idle, okay, and let it warm up or whatever, okay? We accept that every single day, okay, as good enough. So, let's look at the average internal combustion vehicle. So, if you put $100 worth of gas in your car, $33 worth of it goes out the tailpipe as heat. That does absolutely nothing. Okay? It's wasted energy. It's absolutely nothing. Okay? Because really, what are you doing? You're lighting the fuel on fire. You're lighting your money on fire. Okay? Every time you start up your car. That's the same as like when you buy firewood. I don't understand. You might as well just throw your money in the pit and set it on fire. But whatever. Okay? So you put that in, and you got $33 of it is just going to be heat in spent gases. Okay? They didn't do anything useful. All right? Now, your car generates so much heat because, I mean, what are we doing? Burning gas. It gets hot. Okay? That it has to use 33% of the energy in its fuel to power the heating and cooling system that keeps the engine from destroying itself. Okay? There's a little belt that comes off of the main drive shaft of your engine that runs the alternator and the water pump. Okay? The water pump pumps coolant, that green stuff, okay, all through the engine block, absorbing heat by the second law of thermodynamics, pumps it into the radiator, which then blows the air, the hot air, out into the surroundings, helping to cool the engine. That uses 1/3 of the energy your car generates. Okay? That whole system. The drivetrain, that would be all the moving parts. Okay? That number could be higher if you have a four-wheel drive or an all-wheel drive vehicle because it's got more driving parts. Okay? But the drivetrain is generally 10%. That's just energy loss because of moving parts. Okay? Your accessories. That's things like power windows, power door locks, windshield wipers, defroster, rear window defroster, radio, interior lights, headlights, fog lights, brakes, brake lights. Anything that basically runs on electricity, okay, is going to use about 4% of the energy in your fuel. And that's on a, average vehicle. If you've got a vehicle that's got a, 24-inch, touch screen on the front, like some of them have now, it seems like there's a giant TV in the front seat. Okay, that can use more energy. If you have one of those stereos that's like a moving rave, I know the mobile rave goes by my house all the time. Does he go by your house? He sounds like this. As he goes by? Yeah, I don't know. He goes by my house all the time. Okay, if you've got like a stereo like that, that number could be higher. Okay, I know that when I was teaching in Lloydminster before this, every year we had the kids would have a car show. And this one kid had this stereo that used so much power, he had to add a second alternator to the serpentine belt to make more power, because his stereo would literally cause the engine to stall if he didn't push the gas down, because it would draw so much power. So he had to put a second one in. So he was generating so much electricity that, he needed so much electricity, this number was probably double. Okay, so it might have been 8% in his little Rustang, okay, as he called it. Okay, he had like $12,000 worth of stereo equipment and a $2,000 box body Mustang, okay, 4-cylinder, not a cool one. Yeah, it was a cool stereo. He would do this thing called the loony dance. He would pop a loony onto the top of the car, and then he would crank the stereo, and the loony would literally dance on the top of the car from the vibrations, until the day he turned it up too loud, and the back window, because the subs were facing the back window, and the back window just went and spider web. His reaction was priceless though. Oh, cool. I was like, oh man, you know how expensive that window is? Anyway, those take energy. They take energy from your fuel. Internal friction, 6% loss. Okay, any moving parts other than the ones already previously mentioned. Okay, what's left is the useful energy that propels the automobile forward. 14, 225. You have a hybrid car, probably a little higher. If you have an electric car, that number is a lot higher. Okay, now, I'm not saying everybody needs to go out and buy a Tesla. Okay, I'm not saying that at all. Okay, all I'm saying is electric motors are more efficient than internal combustion engines. In the end, you get energy from the same place. Okay, you're either burning coal, okay, to make electricity to charge your Tesla, or you're putting gas in your car. Okay, but in the end, you have to get to work somehow, and you don't get to do that for free, unless you park your car in front of City Hall. Right? If you park in front of City Hall, you can charge it for free. Anybody notice that? There's charging stations, and the new library too also has electric vehicle charging stations. So I guess if you buy an electric car, they're encouraging you by giving you free gas. I want free gas.
Yeah.
Whatever. Not my decision. All right, so does that make sense? Okay, so yes, an electric vehicle by no stretch of the imagination is way more efficient. Okay, it's way more efficient. So if I drive an internal combustion engine to work, I might use, let's just make up a number here, but like 10,000 joules of energy. It's way more than that. I'm just picking a number. Okay, an electric vehicle will probably use 1/3 of that. Okay, it does the same job. It gets me to work, but because electric motors are more efficient, it will use less energy. Okay, so while it still has to take power from the grid, and the grid is powered by combustion of fuel, it is going to use less. Okay, so if you're wanting to save the environment, that's a legitimate way to save the environment. Driving an electric car will save the environment from greenhouse gas emissions. What's the drawback of an electric car in terms of the environment? Have you ever seen a lithium mine? Okay, Like, people complain about the oil sands operations in northern Alberta, but if you've ever seen a lithium mine, that makes it look like Greenpeace threw a party, okay? Like the oil sands make it look like Greenpeace threw a party, okay, compared to what a lithium mine looks like. They are literally just a strip mine, okay? A big, big hole in the earth. So there's that side of it. You do have to, you know, consider that when you're choosing your cars. You're doing the right thing, just make sure you're doing it for the right reasons and understand you're kind of trading impacts a little bit when you do that, okay, just from a, you know, from an environmental perspective. But yeah, they're more efficient. There's no doubt about it. Okay, you certainly would save money on gas because with an electric car you never buy any. Okay, but your power bill will go up, but not by as much as the gas would cost you. Okay, is that making sense? All right, so when we're doing an efficiency calculation, which you're not going to have to do on your unit exam, okay, but just for argument's sake, efficiency is the work the machine does divided by the energy you had to put in to do it. Okay, it's a percentage, just like a score on a test. Okay, it's how many you got out of how many you could have got or how many you did. Okay, so efficiency is the same way. How much work was actually done divided by how much energy was actually needed to do it. Okay, and it comes out just like your percentage comes out on a test. So if it was running at 75% efficiency, it comes out at 0.75. Okay. Everybody all right with that idea? Okay. Okay, so like we said, systems with moving parts are always going to lose some energy as heat. Okay, lots of kind of studies and technology related to efficiency has to do with not so much limiting that heat, it's always going to be there, but capturing it and making it do something useful. Okay, and I think I told you about this before in this unit, but in a lot of electric vehicles and hybrid vehicles, there will be thermocouples, okay, the thing we talked about the first day, embedded in the brake rotors. Okay, thermocouples turn heat or thermal energy directly into, oh, nobody remembers, okay, better know this. Okay, a thermocouple turns heat directly into electricity, right? So when you apply the brakes and you generate heat, some of that heat is actually going to be turned back into electricity, which goes back into charging the battery. Right? So they're looking, you know, if you're looking to increase the efficiency of something, sometimes that involves capturing the waste, okay, or the heat, okay, that's generated. Right? So no system will ever be 100% efficient, okay, because there's always going to be moving parts. There's going to be a loss of energy. Okay? The other way to make a process more efficient is to reduce the number of steps. Okay? Because anytime you're converting energy from one form to another, energy is going to be lost. So the more energy conversions there are in a process, the more opportunity there is to lose energy. Okay? So if we're looking at like the process of getting electricity to your house. So let's say you want to make like a milkshake. So you got a blender at home. You just plug it into the wall and turn it on. Don't really think about it. Okay? But there's a lot of processes that go into delivering that electricity to your house. And every single process results in some energy loss. So you start out at the power plant. Okay? And we'll simplify it by saying we're starting there as opposed to looking at how we got the coal there in the first place. Okay? So we're starting there and we're either burning natural gas or coal or some fossil fuel to make heat. Okay, so there's our first energy conversion. We're converting chemical energy into heat. Okay? Then we use that heat to increase the thermal energy of water. Okay? We use that heated water or steam to turn a turbine. Okay? The turbine turns an electric generator. Okay? The generator sends electricity through a transformer. Okay? That transformer sends the electricity through wires to your house, where a step down, okay, converts it back into useful voltage for your house. Okay? Then it goes into your house, where your blender converts it into mechanical energy. It's converted 7 times on the way to your house. Every one of those times, energy is lost. Okay? Is there ways to make it more efficient? Okay. If there were ways to eliminate some of those steps, yes, there would be. Okay, so we look at different ways to generate electricity. If we're looking at, not using fossil fuels to generate heat and going directly to mechanical energy, that's more efficient. So the wind farms down in Pincher Creek are more efficient because they're going mechanical energy to the generator directly rather than converting it to heat, heating water, turning water to steam, and then turning a turbine with the steam. They're eliminating some of the processes, so they're more efficient. Okay, a solar panel, okay, turns solar energy directly into electricity. That's more efficient. Okay, that's a direct conversion to electricity as opposed to a bunch of transformations in between. Okay. Do they generate as much? Are they as consistent? That's the problem, right? They're great in terms of their efficiency. All of those renewable energy sources are way more efficient. A hydroelectric dam is way more efficient, okay? But the issue there is it always sunny? No. And here's the problem with solar generated electricity. You need more of it when it's not sunny. Okay, so you've either got to have a way to store it from days when it was sunny and people didn't use as much, so that it's there and can be provided on days when it's not sunny. Okay, using solar generation in Alberta is great in the summertime. Okay, when we get 20 hours of sunshine and it's clear, okay, and all of that. This time of year, just think today we're going to get the sun came up at 8:30, it's going down at 4:20. Okay, we're getting less than 8 hours worth of sunshine today, and that's if no clouds come up. Right? That's not great because that means we have 16 hours where lights have to be on, okay, or things, the furnace has to run or the whatever. Okay, we're not getting a lot of generation out of that, so there either has to be ways to store it, okay, so it can be accessed when it's needed, or you have to have something to supplement it, like a fossil fuel fired power plant. Okay? Wind power, same thing. I mean, it's great when it's blowing, okay? But my family's down in Pincher Creek lots of times, and there's lots of times where those windmills are going really, really fast, and there's sometimes where they're not moving at all. Okay, and we always remark on that when we're driving down there. Oh, they're making a lot of power today, or oh, they're not making any power today. Okay, so it's not always as consistent. Okay, so that's kind of the drawback of those more efficient ones is, are they as consistent? Are they as reliable?
What would you say about the dam kind of water power?
Well, a dam is going to be, for the most part, pretty reliable. The problem with it, there's a couple of problems environmentally speaking with a dam. It produces obviously no greenhouse gas emissions, that's its benefit. But it is disruptive to any species, fish species that have to spawn and get past the dam. Once you build the dam, fish don't jump the dam, right? It also changes the flow. So anything above the dam is flooded because the dam is holding back the water, and anything below the dam, the flows are variable. Okay, I don't know if you've ever seen this in the Bow, but the Bow has several dams on it, but the last one, there are some times where the Bow is a raging torrent, and then the next day, you can walk across it, right, and not get your chest wet. Right? It just depends on how much they're holding back and how much power they're generating, and that's true anywhere. Anywhere where there's a hydroelectric dam, the tailwater part after the dam is going to be variable, and that can have detrimental effects on fish species that are native to that area. So that's the drawback to a hydroelectric dam, right, is the way it changes the flow of a river, the way that it affects the fish species, the other aquatic species that are there can all be greatly affected by that. Okay, but it is reliable, provided you always have that water. There is a concern obviously with the source of the water, right? If we get too much melting of the glaciers, then there may not be enough water coming in all the time to power the dam. All right, other questions on that? Those are good questions though. Okay, so basically we just need to know, okay, what efficiency is. Like I said, we're gonna go over a couple of calculations, but you're not gonna be asked to do one on the test, so mostly you just need to understand what efficiency is, okay, how we can make it better, okay, stuff like that. So just some typical things here. Automotive internal combustion engine, 12. I'd say now it's more like 15 to 20 to maybe even 25. Hybrid vehicles are more prevalent. Okay, and they're a good choice. Okay, how many people have a hybrid vehicle? Anybody in here have one? Okay, we're getting our first one next spring when they finally build it. There's a real shortage of vehicles right now. If you're trying to buy a new one. But yeah, so they're more efficient because they will use a smaller internal combustion engine that is assisted by electric motors. Right? So normally when you would, in a regular internal combustion engine, press down the gas, it would use more fuel, it's a bigger motor to power you forward. Okay, now you push down the gas, electric motors kick in, so the smaller engine doesn't have to work as hard, which saves fuel. Okay, and then your power system charges the batteries that assist the electric motors. Okay, they're great as long as you're using them in the right conditions. Okay, all highway is not a way to make use of a hybrid vehicle. Okay, because all highway, the electric motors don't kick in very much because they're only going to kick in when the car is under load, that is working hard. So if you go up a hill, they'll kick in. But if you're just driving on the highway, they barely kick in at all. So it's great if you're in a lot of commuter stop and go traffic, which is why they're very popular here, because people commute to Calgary a lot. Okay? Same with electric vehicles. As long as you don't have to worry about going more than the range of the battery, okay, they're a great choice. Awesome if you're only going into Calgary and back every day. Electric vehicle is a great choice. You're not going to run your battery out, okay, in that space. If you're looking to go cross country, okay, in like 5 days, an electric vehicle is not a good choice. Okay, because after 600 kilometers, you're going to have to stop and charge it for 3 hours and go again and whatever. So, you know, that's the advantage of an internal combustion engine. I stop at the gas station after I've driven 1,200 kilometers on my super giant tank. Okay, I put, you know, $500,000 worth of gas in it, and I drive another $1,200 or 1,200 kilometers. Okay, and then I fill again. But I don't have to stop for very long. It seems like a long time when you watch the money go in the pump, but it's not as long as stopping to get powered up. Okay, electric engines up to 95% efficient. Now the reason an electric motor is more efficient than a gas motor is it doesn't use heat. Okay, it doesn't use heat to turn it. It uses magnets, and those magnets don't touch each other. So there's very few contact points in an electric motor, and the fewer contact points there are, the less friction there is. Okay? So they run far more efficiently than metal pistons going up and down inside a cylinder, okay? Metal on metal all the time. Meanwhile, fuel is being exploded above them. Okay? So it's more efficient than that. Okay? A steam reciprocal engine, okay, 50 to 75% efficient. A steam turbine engine, up to 40% efficient. These are not things that you or I would be using to power anything, but if you are on, let's say, a nuclear-powered vessel, like an aircraft carrier or a submarine, these are your source of drive power. Okay? You'd have your nuclear reactor making heat that evaporates the water and turns the turbines, okay, that power the sub forward. Okay, all right, let's have a look at this question right here. Okay, but I'll erase my work first. Okay, so this is how an efficiency problem would sound. Again, you're not going to have to do one on the test.
Do we have to know like those percentages, like how, like
No, I'm just giving it. I'm just putting it out there so people have an idea of, okay, this thing is efficient versus this thing, right? And I'm not in any way trying to knock internal combustion engines. Okay, I drive a V8 powered truck. Right? So I'm not that guy who's saying, you know, internal combustion is bad. Okay, I'm also not the guy who's saying electric cars are bad. They both have their purposes, and they both have their uses, and they both have their drawbacks. Okay? I'm just presenting all of it, trying to be as neutral as possible, even though I'm that guy who likes the V8 power. Okay, so crane lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.30 times 10 to the 4 joules of work, or mechanical energy input. Okay? While doing 8.0 times 10 to the 3 joules of useful work, or mechanical energy output. Okay, so efficiency is useful work, or work output, divided by energy input, right? If you're ever looking at a question and going, I don't understand which one's which, the smaller one always goes on top, okay? Otherwise, you're gonna get a number greater than 1, which means you're making energy and violating the first law of thermodynamics, okay? So, the work, the useful work is the 8,000 joules, okay? The work input is the 23,000 joules. Okay. So it's going to come out to 34.8%. Right? Now, where's a lot of that energy going? I mean, all we're doing is using a crane to lift a pallet of materials from the ground to the second floor. Sound, heat, okay? Those would be your two big ones, right? I mean, is a motor loud? Like when we went over the internal combustion engine's efficiency, we never mentioned how much, never even mentioned how much sound it produces. Okay, I mean your car has to have mufflers on it so that you aren't deafened by driving it. Okay, they're that loud. I mean you've heard the other guy, right? There's moving rave guy, and then there's like redneck pipes guy. Okay, he drives by my house too. He must live in my neighborhood. Okay, but he's got like no exhaust system on his truck, okay? Yeah, and it makes that horrible sound like moving thunder, okay? Unless he's really revving it, and then it's just like this horrible snapping sound.
From my house, you can hear them going, like accelerating up the highway. That's
Yeah,
about there.
that's where we hear him going up the highway. Yeah, that's where the speed limit goes from 60 to, well, it's not supposed to do that till further away, but they start earlier. Yeah. Hear that guy. All right, so 34.8% is what this comes out to, okay? We're losing, so it would actually on your calculator come out to 0.348, okay? But that's 34.8%. Okay, everybody okay with that one? Okay, like I said, you're not gonna have to do any calculations on your test as long as you understand energy input, energy output, or useful work, okay, and how it relates to efficiency. Okay. I want to try at least 2 more of these law of conservation of energy questions today, because obviously there's one on your exam tomorrow with big marks, and I want you to get all those marks. All right, so write this one down, give it a try. Car drives off a cliff at 25 meters per second. Okay, when it strikes the ground below, it is moving at 53 meters per second. How high is the cliff? Okay, so looking at this one, so there's our cliff. Very intimidating looking. Okay, car drives off the cliff at 25 meters per second. So that's going to be our initial speed. And then it's going to go all the way down to the ground. Okay? And when it gets to the ground here, it's going to be going 53 meters per second. So that will be our VF. What's our final height? Right. Okay. Energy top and bottom the same? We have to assume so. We're not told that there are any other forces or anything like that. Once the car goes off the cliff, the only thing acting on it is gravity. Okay, so our energy initial equals our energy final. Okay, and we can say we've got initial potential, because obviously we're on a cliff, so we've got some height that we have to find, plus initial kinetic, we're moving at 25 meters per second, and then at the end, we would only have kinetic, because we're talking about the impact on the ground. Everybody with me so far? Okay, so now I can put in my formulas, m times g. Actually, before I do that, I want to find h initial, which is part of this term. So I want to get this term by itself. What do I have to do with ek initial? Okay, so EP initial equals ek final minus ek initial. Now we can put our formulas. M times g times h initial, which is what I'm looking for, equals 1/2 mvf squared minus 1/2 mvi squared. What's in every term? Right. Do I need it? if I was uncomfortable because I wasn't given it, I could use any number I want. Okay? You can make up a number, and it won't matter as long as you use the same number for every m. Okay? So, we've got that taken out. Now we're manipulating for HI. So what do I do with G? All right, so G comes over there. Our initial height then will be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Oh, that's a tall cliff. Okay, 111 meters high. Okay. That was an exam question about 7 or 8 years ago. Give you some idea what I might ask. Okay. I flip-flop between asking for a height and asking for a speed. Okay. It's basically like that. Okay, give that one a try. Okay, skydiver jumps out of a plane moving at 90 meters per second, 10,000 meters above the ground. How fast will the diver be falling when he is 8,000 meters above the ground, assuming he has not opened his chute? Okay, because if he opens his parachute, he no longer accelerates due to gravity. We bring in a force, it becomes a work energy theorem problem. Okay, so that's what I'm saying, he did not open his parachute. All right, so if a person jumps out of a perfectly good aircraft, okay, they will be at 10,000 meters, so that's my initial height, moving at an initial speed of 90 meters per second. Okay? And we want to figure out how fast they're going when they are 8,000 meters above the ground. So it's basically the same thing. It's all patterned. Okay, we just have to be able to figure out what it is we're solving for. So there's no mention of any other forces. In fact, they specifically said the chute's not open. There's no friction. It's okay, just gravity. So we have both kinds of energy at the beginning, EP initial and EK initial, and we have both kinds at the end. Okay, what I'm looking for is part of which one of those? EKF, right? I'm looking for the final speed. So I need to get that by itself by doing what with EP final? Right. Okay, now we can put in our formulas. So M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. All right, so now we've got all our formulas in. Didn't tell us the mass of the skydiver. It's irrelevant anyway. Okay, so I take that out. I just need to get VF by itself and not squared. So what do I do?
Square root.
Before I square root.
Divide by
1/2. And then square root. Okay, so my final setup here will be that VF equals 9.81 times 10,000 plus 1/2 times 90 squared minus 9.81 times 8,000 divided by 1/2. That's fast. Okay, so if you fall 2 kilometers, okay, with an initial speed of 90 meters per second, you will be moving at 217.6 meters per second, and you are still 8,000 meters above the ground. Okay, so this is kind of like the Red Bull guy. Did I show you that guy, Felix Baumgartner, that jumped from orbit? Yeah. Okay, like he broke the sound barrier, okay, falling. Right, that's 300 meters per second, 340 meters per second. Okay, so you'd be going really fast. Okay, now he had a special suit, and he did that much higher in the atmosphere where it didn't like destroy him. Because breaking the sound barrier near ground level in a thicker atmosphere has detrimental effects on the structure doing it generally, unless it's got the right shape. All right. Questions on that one? All right. I'll take questions about the test if you got any.
We can come early, right?
Yes, you can come here early. I will allow you guys to start at, let's say, 10 after. Okay, so if you're here at 10 after, right, I will give you your test and you can get started, and I'll give you an extra 20 minutes or so because we're going to lose 5 minutes to Canada morning exercises and stuff. So let's start at 10 after, and then you have till the end of class to write it.
This is just like clarification. How do you tell the difference between if you're supposed to do like a work energy theorem question and then like a law of conservation of energy question?
If force is mentioned, it's a work energy theorem question.
Okay.
And if there's an obvious change in energy that's not caused by gravity. Okay, so in a question like this, gravity is the only reason kinetic and potential are changing, but the mechanical is staying the same. In a work energy theorem problem, it's very obvious that the mechanical energy is changing, and there's usually only one type, right? So it's just speeding up, it's not falling, okay? Or it's just being lifted and it's not speeding up. Only one type of energy would change. In a law of conservation of energy question, they both change because they're changing into each other.
If we get confused, can we have one free pass if Jesus is the answer?
No. Jesus is always the answer. He's just not the right answer on a physics test.
Okay.
I don't know if you said this, but how many of these questions do you have with us?
One.
Oh.
But it's worth, I want to say 6 marks.
Okay.
Do we have to write like a sentence?
No, just
No.
have your answer. Now, on that note, because that's a good point, if you guys can do me this big favor on your test, when you write your final answer, this came out to 217.6 meters per second, circle it. I mean, you get full marks if your answer is right. If I see the right answer, it saves me a lot of time. Okay? I also then know where your question ends, and if it's wrong, I know how to work. I know where to work backwards. Okay. Now, for me, most of the time, when I look at an incorrect answer, there's basically like one correct answer, and then there's like 3 incorrect answers. It's basically the other 3 ways people who misunderstood the question might do it, and these are the answers they would arrive at. So if I see that number, I can work back and give you the part marks, okay, that you would deserve. Right? So on that note, also show your work. Okay? Don't just write a number in and circle it, because if it's wrong, I'll circle it with a bigger circle.
Okay, and what are the like equations that we have to do the positive or negative, or should we just do it in all of them? Like, is there
Anything that's a vector quantity would need positives and negatives. So if you had a position time graph question where the object went backwards and forwards, then direction would be important. Same with the velocity versus time graph. If there were positives and negatives, it would be important if it's asking for a vector quantity.
And would like this equation need one because it's typically like
No.
going down?
This is all scalar, right? Work is scalar, energy is scalar, and in these, it's not velocity, it's speed, right? So they jumped out at a speed of 90 meters per second, right? They actually weren't falling at 90 meters per second. When they jump out of a plane, they're moving horizontally at 90 meters per second. It's all part of their energy, though. Okay, what else?
On a question that is vector and it's all in the same way, we would just all make it
Then
positive?
it can all be positive. So if you got an object that's falling, okay, you don't have to put in positives and negatives. That said, if at the end of that question it says, what is its final velocity, you would still need to indicate that it's down, right? You don't necessarily have to show that mathematically because everything is down, but you still have to give the vector on your answer, right? Okay, what else, guys? Don't be afraid to ask. There aren't any silly questions. Okay, this is your test. Whatever you want to ask, you ask.
Are there any questions on it that include negatives? Like
Yes.
opposite versus-
I mean, vectors are part of this unit, so there are gonna be some, yeah, you're gonna have to use the positive and negative.
Oh, sorry, and as well, do we have to know anything about the people for the multiple choice or?
Can we get half marks on multiplication points for participation?
Half marks. I give part marks, like if it's a 5-mark question and you did 3 of the steps correctly, the last step you did incorrectly and got the wrong answer, you got 3 out of 5.
No, like on the multiplication. You get like half mark for participation.
On the multiple choice
Yeah.
lead? No. I just score that with my phone. Scans it. That's it.
And then like the V, like and then like D over T questions, those are only in the multiple choice, or are they also?
Yes.
Yeah.
They are only in the multiple choice. It's like simple. There's even a simple acceleration one in the multiple choice, which I told you up front. I'm not telling you anything new. If you think you're pumping me for information, I'm not telling you anything different. My story is very consistent. Okay, what else, guys? Okay, we had a short class on Friday to do the unit exam review, so you didn't get a lot of time in class to kind of work through the review sheet, so giving you a little bit of time here now to do that. You got about 20 minutes or so left here. Maybe some more questions will come up as you look at some of those problems or go through your notes or whatever. But it was my intent to have kind of a full class length of time for you to prepare. So this is the 20 minutes you lost last week. Okay, if questions come up, let me know. You can.